In this video, we'll continue to look at the members subjected to bending, and we'll look into some other modes of failure than what we look at the previous video. So in the previous video, we have looked into the member section, nominal section capacity that takes into account the yielding of the bending members or the local buckling in the compression flanges in the beams. In this video, we'll look into another mode of failure that we can see in steel beams, and that mode of failure is called as the lateral torsional buckling. And as you can see in B here, as you can see, it is a lateral or flexural torsional buckling. You can see it is a top view, and you can see that the beam has buckle laterally, and also it will be twisting as well. So we'll look at the mode of this mode of failure in this video. So as you know, beam carries the transverse loading. It can be uniformly distributed load or the point load as shown in the figure. Now, because of this transverse loading, the beam will be bending, and you know that there will be compression at the top and the tension at the bottom. Now, if we take the cross section of this I-beam here, and we see that there will be the compression in the top section above the neutral axis, and the beam will have tensile stresses below the neutral axis. Now, for the bottom half of the section where it is in tension, we don't have any issues with that, because tension, the steel members do not buckle. But the top half where it is subjected to compression force, as we know, in the slender members, the compression force can cause buckling. So we have two different kinds of forces here. So the top portion of the steel section is subjected to compression force, and that is trying to buckle the beam, and the bottom portion of the beam is in tension, which is trying to resist the buckling. So there is a tendency of buckling in the top half, and there is a resistance to buckling in the bottom half. Because of this force, mechanism here, the beam itself will buckle laterally and twist as well. So the compression flange of the beam acts like a column and will tend to buckle sideways, whereas the tension flange will resist the buckling, and that's what caused the lateral torsional buckling in the beams. Now, the lateral torsional buckling will look like this one. So as you can see here, the top portion, which is in compression, has buckle in this beam, and the bottom portion, which is in tension, is trying to resist that buckling. And you can see that the beam has moved laterally, has buckled laterally, and there is a twisting in the beam as well. There is a torsion as well. So this is a very common mode of failure in beams where we do not have any lateral bracing or restraining against the lateral movement or rotations. And you can have a look at this video given here. You can scan it through your mobile device on the QR code and look at the video which demonstrate how the lateral torsional buckling occurs. Now, in the previous video, we look into the nominal section moment capacity, that is MSX if it is bending about x-axis, or MSY if it is bending about y-axis. Basically, it is a function of yield stress of the steel multiplied by your effective section modulus, that is ZEX or ZEY, right? That takes into account the yielding of the whole section, that is, the whole plastic hinge is developed on the overall section, and also it takes into account the local buckling of the beam section as well. But now we are looking at this nominal member moment capacity, which is denoted as MB. Now, nominal member moment capacity takes into account the possibility of lateral torsional buckling in the beams. So the nominal member moment capacity, or written as MB, is a function of section capacity, that is, you already find out your MS capacity, flexural or lateral torsional buckling resistance, that is the beam action, the resistance against the lateral torsional buckling, and lateral buckling resistance, which is the column action of the member. So the nominal member moment capacity, MB, depends on all these three things. So let's have a look at how we find the nominal member moment capacity that takes into account the lateral torsional buckling. Now the nominal member moment capacity MB about the major axis, that is if it is bending about the x-axis, as you can see here, the major axis is about x-axis, the minor axis is about y-y, is given in AS4100 in clause 5.6.1.1 by this equation. So here MSX is nothing but the nominal section moment capacity, which we already found out for the bending about x-axis. Then we have two parameters here, alpha s and alpha m. These parameters are there to take into account the lateral torsional buckling into account. So alpha s here stands for the slenderness reduction factor, which is given in clause 5.6.1 again. And alpha m here stands for the moment modification factor, which is given in table 5.6.1. So alpha s and alpha m takes into account the lateral torsional buckling mechanism into account. So we'll be using these two factors and multiply it to the nominal section moment capacity MSX to get our member moment capacity for the given section. As you can see in the lateral torsional buckling, you can see that the member has buckled laterally and also it has twisted as well. So this is the kind of failure mechanism we can see in the beams which is not laterally braced or which do not have rotational resistance along the beam. Now one point to note here is that lateral torsional buckling does not occur in beams bent about their minor axis or y-y axis. What it means is that the lateral torsional buckling only occurs for the beams that is bending about the major axis or x-x axis. When it is bending about the major axis, x-x axis, then there is a possibility of lateral torsional buckling about the minor axis. It can buckle about the minor axis, which is the weaker one, right? But if it is bending about the minor axis to start with, then it cannot have a lateral torsional buckling because the lateral torsional buckling has to occur against the stronger axis, which is x-x axis, and it doesn't occur that one because it is bending about the minor axis or the weaker axis, so the bending will be predominant than the lateral torsional buckling. So the lateral torsional buckling only occurs when it is bending about the major axis, that is about x-x axis. If it is bending about the minor axis, there will be no lateral torsional buckling. It will just be bending about the minor axis. Now that means lateral torsional buckling cannot occur if the bending is about the minor axis. In that case, so if it is bending about the minor axis, if the loading is such that the bending is about the minor axis yy, then the major axis or the stronger axis xx is pretty strong, so there it can resist the lateral torsional buckling, right? It will the bending about y-axis is more predominant in that case. So in that case, your capacity is simply phi MSY, where MSY is the nominal section moment capacity. You just have to find the nominal section moment capacity about y-y axis and multiply with the phi. That is your design moment capacity for bending about minor axis. There will be no lateral torsional buckling happening there. And also there will be no lateral torsional buckling happening if it is continuously laterally restrained. That means if the whole beam is continuously restrained against lateral buckling, then there will be no lateral torsional buckling. And if it is bending about x-axis and on top of that it has the continuous lateral restraining, then there will be no lateral torsional buckling. For example, if it is bending bending about x-x axis like this, but there is a continuous lateral torsional restraining because of the concrete slab on top of it, which is connected to your steel beam, then the steel beam cannot move laterally or cannot buckle laterally. In that case also there will be no lateral torsional buckling. As it is bending about x-axis, your capacity will just simply be MSX multiplied by phi, where MSX is again the nominal section moment capacity. So we just have to find out the nominal section moment capacity, and that will be your capacity of the beam. So there will be no lateral torsional buckling possible in that beam as well. So these are the two cases where we do not have to consider lateral torsional buckling, but other cases we have to calculate the possibility of lateral torsional buckling as well, and their capacity also we have to calculate. Now this is how the continuous lateral restraining in a beam looks like. So as you can see here, it is bending about x-axis. You are loading on top planes here, and it will be bending about x-axis because of this loading from the top. As you can see, the compression is on the top, tension is on the bottom, but as you can also see that there is a concrete slab on top of the steel beam, and it is connected using a shear connections to the steel beam. So it is fully laterally restrained. That means there is no possibility of this beam to move out of plane, to buckle out of plane. So there won't be any lateral torsional buckling in this beam. It is fully or continuously laterally restrained. So in this case, your capacity is the nominal section moment capacity about x-axis. That is what you have to find out, and that will give you the capacity. So there is no lateral torsional buckling in this case. Now, if there is a lateral torsional buckling possibility, then we have to find out the nominal member moment capacity. So other than what we discussed before, if it is buckling about y-axis, if it is bending about y-axis, or if it has a continuous lateral restraining, we do not have to consider the lateral torsional buckling. But for other cases where it is bending about the x-axis and do not have continuous lateral restraining, we have to consider the member moment capacity MB. Now to find out the nominal member moment capacity MB, we have to calculate two factors as we described earlier, and MB we know that it will be found out using the two factors alpha S and alpha M, and we multiply it to our MSX, which is the nominal section moment capacity. So we have to find out now alpha S and alpha M. And alpha S, as we defined earlier, it is a slenderness reduction factor, and alpha S accounts for the tendency of the section to buckle laterally. So it takes into account the tendency of the section to buckle laterally. The more slender the beam, the higher its tendency to laterally buckle, and hence the alpha S will be lower for that. So we are reducing the capacity, taking into account that the beam is more slender and there is a more chance of lateral buckling of that beam. So alpha is a function of the moment ratio, which we take it as MSX over M naught. MSX is again the nominal section moment capacity, and M naught is a reference moment, right? So it is alpha S factor is a function of MSX and M naught. So let's see how we find alpha S factor here. So the clause 5.6.1.1, if you look into the clause in AS4100, you can see that alpha S is a function of MSX over M naught, where MSX is a nominal moment capacity of a fully restrained section. If there was no lateral torsional buckling, MSX is your capacity, which is nothing but Fy multiplied by Zex. And M naught is a reference buckling moment. So once we know these two parameters, you can find alpha S. Now we already know MSX, how to find MSX, but we need to find out M naught, or the reference buckling moment. So let's have a look at how we can find M naught. Now again, in clause 5.6.1.1, it gives us the formula to find out M naught, that is the reference buckling moment. As you can see here, there are different sections in this equation here. Now, for the calculation of reference moment, this equation would be familiar to you, isn't it? It takes into account the buckling or the column action in there, right? It is very similar to the Euler formula. This takes into account the twisting of the beam, and this takes into account the warping of the beam. So as you can see, the reference moment takes into account all this phenomenon into account in this equation. So there is a buckling included in there, there is a twisting, there is a warping of the section as well. So all of that is included in that equation, and all of the properties that you mentioned here is for that particular section that we can find out from the design properties from the one steel table or the manufacturer's table. So here E is the Young's modulus of steel, which we know is 200,000 megapascal. G is the shear modulus of steel, which is 80,000 megapascal, and J is the torsion constant, which is given in one steel table. IW is a warping constant, which is also given for the section in the one steel table. What else? IY is again the moment of inertia about the minor axis, because it is buckling about the y-axis now, so it is also given in one steel table as well. So here I missed to write IY. And it is also given in one steel table as well. And another parameter given here is LE, which is the effective length of the beam about which the buckling can occur. So we'll discuss about how to find the effective length LE. It is different than the effective length that you use in the column design. So LE is effective length for the beam sections about which the buckling can occur in that section. Now in this equation, as I said, LE is the effective length of the beam, and it is given in clause 5.6.3 in AS4100. So it takes into account three different parameters here: KT, KL, and KR. L is the length of the beam, the original length of the beam, and we multiply with KT, KL, and KR factors to take into account the possibility of twisting, lateral buckling, and also where the load is acting as well. So as you can see, KT is called as the twist factor, which depends on the flexibility of the wave. So can the section twist? That is what taken into account in KT factor. It is given in table 5.6.31. KL takes into account the load height factor, which is given in table 5.6.32, and KR is the lateral rotation restraint factor, which is given in 5.6.33. Can your beam rotate at the ends? Laterally, can there be some lateral rotation at the ends? That's what is taken into account by KR. So once we obtain this KT, KL, and KR based on your restraining of the beam, what is the restraining condition of your beam, we find out KT, KL, and KR, and use that one to multiply with the length of the beam itself. You get the effective length. Plug it back into this reference moment equation, you get M naught, and again use that M naught back into the alpha S equation to get your alpha S factor. Right, so that's how we have to go ahead with that. So let's discuss on what are these KT, KL, and KR one by one. So before we go into that, let's look at the effective the length of the segment itself. So length of the beam is between the restraints. So for example, in this case, here's number one. As you can see, there is no restraining in between the supports here. The support is here and here. It might be fully restrained at this point and fully restrained at that point. So you can see that the beam can buckle the whole length. The whole length of the beam can buckle. So your L equals to the big L here. So it's the complete length of the beam. Now in the second case, there is some restraining at the middle of this beam. It can be because the purlin is connected to your beam on the top, and also there might be some fly braces connected to the bottom flange as well. So if it is connected like that, it might be partially restrained or fully restrained at this point. Then you can see that the middle point cannot move laterally. So the length of the beam that can buckle now is only L by 2 here, or L by 2 on the other half as well, right? The buckling will occur like this one. So in this case, your L would be L by 2 only. So you have to look into the half section. So the bigger the length, there will be more lateral torsional buckling. So if we have more bracing like this one, if we have more resistance against lateral torsional buckling in the middle sections of the beam, so your L will be reduced, and that means your the capacity will increase. That means the chance of lateral torsional buckling will reduce. Good. And now in the third case, we see that there are two intermediate restraining here. It might be again purlins connected to the beams or fly braces that prevents the lateral movement at that point. So it might be F or P, partially or fully restrained at that point. And then your length of the beam segment is reduced to L by 3. So your length of the beam segment is only L by 3 in this case, right? So depending on location of or the existence of this restraining conditions in the beam, we can have a different length segments for the beam that we have to use for your effective length, right? So your L for different cases can be different for that beam. Now, also, as we discussed before, if it is a continuously lateral restraint, like what we discussed before, if there is a concrete slab on top of the beam on the full length of the beam, and it is connected with the beam with the shear studs, so then there is no possibility of this beam to have lateral movement. So it is continuously laterally restrained. So in that case, practically the effective length LE is 0 in this case, isn't it? Because it cannot buckle laterally. That means, what it means is that your alpha S factor becomes 1. That is the best case scenario. So when alpha S is 1, it is the best case scenario that will give you the maximum capacity. But when there is a possibility of lateral torsional buckling in like these ones, then alpha S becomes less than 1, and it will reduce your capacity. The more the effective length of the beam, alpha S will be further smaller, and it will reduce your capacity furthermore, right? But when there is a continuous lateral restraining, your effective length LE becomes 0. That means there is no buckling length there. No length of the beam will buckle. So that is LE equals to 0. That means alpha S parameter becomes 1. And when alpha S is 1, you will have a full capacity in that beam. That is, it will fail by forming the plastic hinge in that beam, right? So that will be your capacity then. So here is an example of a beam, actual beam here. So as you can see here, so in this beam you have at this point there is it is connected to the purlin there, and also the lateral the fly bracing is connected to the tension side as well, right? So this part cannot move laterally. So we can consider this as a fixed section, fully restrained section, and also at this point it is fully restrained. So we will only have to take this length as your length of the segment that to take into account the lateral buckling within that segment only. So we can see that there is a full restraint on these sections here. Good. And at this point, it may not be fully restrained because there is no fly bracing. It is connected to the purlin, but it might be partially restrained at that point. Now, with that understanding, we can look into how to find the twist factor KT. So we use the twist factor KT to calculate your effective length LE. Now again, effective length LE is equal to KT multiplied by KL multiplied by KR multiplied by the length of the segment. Now what is KT here? The KT is the twist factor, which accounts for the flexibility of the wave. So if we look into 5.6.3.1, it shows us for different conditions, restraining condition at the ends, your KT factors will be different, right? Again, the best case scenario is KT equals to 1 here. Now you can see, depending on the condition, so we'll discuss about what does F and L and U means now. So if it is a beam here, and what kind of restraining conditions are at the end. So if it is fully restrained at this point, that is written as F, and if it is fully restrained at both ends, that is considered as FF conditions. So in that case, it is KT equals to 1.0. Similarly, if it is fully restrained and laterally restrained at this point, so that means it cannot move laterally at that point, that is FL. LL means that both the ends are laterally restrained, and FU means that one end is fully restrained and another end is not restrained at all, unrestrained section, then KT is taken as 1. Similarly, if it is FP, that is fully restrained and partially restrained condition, we will take the equation from here, and partially restrained, we will use this equation. Now in this equation, D1 stands for your clear depth between the flanges, ignoring the fillets or wales. So D1 stands for, if it is your I section like this, D1 stands for the clear depth between the flanges. So this is your D1 from inside of the flange to the inside of the flange. That is D1. And NW stands for number of waves. So how many waves are there? In this case, there is only one wave, isn't it? So there's only one wave, that is NW equals to 1. So there might be the cases like your section is like this. So you have two waves here. Sorry, this one and this one. So your NW is 2 in this case. There are two waves for that. And TF is the thickness of the flange, of course, and these are the restraining condition at the ends: fully restrained, laterally restrained, partially restrained, or unrestrained. So these are the notation on that. So depending on what is your end restraint condition, you can use the equation to find out what is your KT. Now, to understand what is the full restraint and partially restraint at the section, we need to understand what is the critical flange first. Now, the critical flange is what is the flange that deflects the farther during the buckling. So it is the flange that will go farthest while there is a buckling occurring. Now, you can see that for a simply supported beam loaded from the top, as you can see here, when there is lateral torsional buckling, you can see the top flange is moving, twisting farthest away from this original position, isn't it? So it has moved quite a lot, but the bottom flange, which is in tension, hasn't moved that much. So the top flange is the critical flange for this case. So the critical flange in a simply supported beam with a downward load is the top flange in compression. So the top flange is in compression, and that has moved the farthest when there is a lateral torsional buckling. It has twisted far away from its original point. So that is what it is, a critical flange for this case scenario, right? Now, if we look into the different case here, it is a cantilever beam, and it is loaded at the end, as you can see here, and the top is in tension, the bottom is in compression, right? In cantilever, the top will be in tension, the bottom will be in compression. And when there is a lateral torsional buckling happening in the cantilever beam like this one, as you can see, there is a lateral, the beam is twisting and moving laterally. You can see that the top tension flange is has buckled the farthest, right? Has moved farthest compared to the bottom one, which is in compression, isn't it? The top one has buckled farthest. So that's why the critical flange is the top flange in the tension member, which has buckled farthest, right? So the top tension flange is the critical flange for the cantilever. Any flange that buckles the farthest is the critical flange for that section, right? So if this end is unrestrained, then when you have a lateral torsional buckling in the cantilever beam, you will see that the top tension flange will buckle the farthest. So that is the critical flange for your beam. Now, if we can restrain this critical flange, and we will be achieving the full restraining. So because the critical flange is the one that will try to buckle farthest, and if we can have some mechanism to restrain this critical flange, we can achieve the full full resistance to lateral torsional buckling. So let's see what are the examples of full restraining. So basically, a restraint that prevents the lateral displacement of the critical flange of the cross section and prevents the twisting of the section is the full restraining, right? So any restraint mechanism that prevents the lateral displacement of the critical flange. So if the critical flange cannot move and twisting of the section cannot occur, we say that it is a fully restrained, and we denote it as F, right? So it can be achieved from any of these mechanisms. Again, this one, as we shown earlier in the rail beam structure, there is the I section is connected to the purlin, and there is a fly braces connected to the tension side. Again, if it is a critical flange, is denoted by C here. So there is no possibility of lateral displacement as well as no possibility of twisting. Then we are saying that it is fully restrained, and we can denote it as F, right? Similarly, in the other condition, as you can see, having another beam connected, the beam connected to the another beam with this bolt connection, then it can, in the critical flange side, then it can provide the full restraining as well. So these are the other examples where how we can achieve the full restraining, right? And again, if the critical flange is connected to the having the fixed connection, and then we are using the bearing stiffeners again, so there won't be any twisting, and also there won't be any lateral movement of the critical flange. Again, it's a full restraining. So these are the different examples of full restraining. Good. Now, how we can achieve the partial restraining? A restraint that prevents the critical flange of the cross section from displacing laterally and only partly prevents the section from twisting. So unlike the full restraining F, partial restraining can prevent the lateral displacement of the critical flange, but only can prevent the twisting partially only. There can still be some twisting happening there. It is called as a partial restraining. As you can see in this example, this is a good one. The critical flange is C here. It cannot displace laterally, but there is some twisting in there, right? So that is called as partial restraining. Similarly, there are other examples in here which we get partial restraining only. So here there is a RC slab on the steel beam, but your critical flange is at the bottom here, and there is no restraining at the critical flange. So it doesn't move laterally, but there will be some twisting happening there, right? So that is a partial restraining P. Similarly, a lateral restraint means a restraint that prevents the lateral displacement of the critical flange without preventing the twisting of the section. So L stands for the lateral restraint. It means that the critical flange cannot be displaced laterally, but the whole section is free to twist. So there is nothing to prevent the twisting. And some examples are here. So there is a connection to the purlin, as we saw in the middle section, but it is free to twist. There is no movement in the lateral direction, but it is free to twist. The twisting can occur. Then it is called as lateral restraining only. So there is no restraining against twisting. Similarly, no restraint or the unrestrained section U, the cross section does not comply with any of this FPL condition. So it is free to rotate, free to move laterally as well. So for example, this end condition here, it is unrestrained. It can move laterally and it can twist without any restraining, right? So that is written as U, or unrestrained section. Good. So as we know all these F, P, L, and U conditions, and we found out what is the condition for your beam, then we can find the KT factors using going back into this equation here. So once we know what is your end condition, so we use that one to find the KT factor from these equations. Now, another factor KL that we need for finding effective length is a load height factor, KL. It depends on where the load is acting on your beam. So whether the load is acting within the segment or at the segment end, and also whether the load is acting at the shear center or at the top flange. So that depends on whether your beam can have a more twisting effect as well or not. So as you can see, again, these are the end conditions. Basically, it means whether the load is acting at the end within the segment, like in a simple supported beam. If the load is acting within the segment, this is the case, and at the end of the beam. So for example, in the cantilever beam, if the load is acting at the end of the beam, this is the case, right? And again, whether the load is acting through the shear center or whether the load is acting just on the top flange of your I-beam, right? Let's look at it now. So if this is a channel section that you have, it is a cantilever channel section, load is acting at the end of the segment. But as you can see, for the channel section, the shear center is at this point. Good. Now, shear center means that if the load acts through that shear center, there will be pure bending and there won't be any twisting. Good. That is what it's called as shear center. If the load acts through the shear center of the cross section, there will be pure bending in the beam and there won't be any twisting. So if the load is acting through the shear center, you have to use this factor, which is basically K L equals to 0, because there is less chance of twisting in that case, right? But if the load is not acting through the shear center, like in this case where the load is just acting on the top flange, it is not acting through the shear center. In that case, your beam can twist as well as bend. As you can see here, the load is acting through the shear, the load is not acting through the shear center. Then you can see the twisting of the cross section apart from bending as well. So there will be a combination of twisting and bending, and that will increase your KL factor. As you can see, if the load is just acting on the KL on the top flange, your KL is more than 1, which will have effect on increasing the effective length and reducing the alpha S factor. Good. So if it is acting through the shear center, there won't be any twisting, so the KL is 1. If the load is acting on the top flange and not going through the shear center, then KL becomes more than 1. That will increase your effective length and reducing your alpha S factor and eventually reducing your capacity as well. Now finally, the KR factor is a lateral rotation restraining. So whether the beam can move laterally at the end or not, that is KR factor. And depending on the end condition, restraint condition at the beam, and whether there is any restraining at the end to move laterally. So if you're looking at the top view of your beam, so if your beam supports are like this, so whether there is a rotation resistance on this end, right? Is there any resistance to rotate the beam laterally? If you're looking from the top, can it rotate laterally at that point? That is called as KR factor. So if there is a restraint at both the ends, you'll have 0.7. If we don't know if any, it's 1. If none, it is 1 again. If there is only at the 1 point, it is 0.85. Right? So the conservative one is to use 1. Other than that, if you know that there is both in our restraint against lateral rotation, you will have 0.70 as a KR factor, which is given in table 5.6.3. Now, once we know KT, KL, and KR, we can find effective length. Now, there is also another 2 tables here that will be helpful when you are designing the beam. Sometimes you don't know when you are designing the beams, you will not know the cross section to start with, so you cannot find the KT, KL, and KR factors to begin with, right? So in that case, when you are designing the beam where you don't have the information of the cross section yet, so you can use these tables from this designer handbook from Gorenk 2005. You can use these tables to estimate the KT, KL factor to start with. Even though you don't have any information, so you can't use the equation. So in that case, what you can do is use these factors. If it is for simply supported beam, start with this KT, KL, and factor. If it is cantilever beam, start with this KT, KL, and factors, and then choose the section, and then come back and use the actual properties to find out the KT, KL, and KR factors. So if you do not have the information of the section yet, use this table to estimate KT, KL, and KR to help you in the design process. We'll see in the examples later on. Now, once we know KT, KL, and KR, so we know that the effective length equals to KT, KL, and KR multiplied by the length of the segment, right? So you can find out what is effective length, and once you know the effective length, you can find out your M naught, and then you can find out your alpha S, right? That's what we are trying to find out, isn't it? It's alpha S factor, slenderness reduction factor. Now, once we know alpha S, the next step is to find the alpha M factor, that is a moment modification factor. So let's look into it. So why do we need moment modification factor? Because our lateral torsional buckling equations is based on that it is a constant moment throughout the section, right? When the beam has a constant moment throughout the section, then the top flange will be or one flange will be in compression uniformly, and the one flange will be in tension uniformly, right? So in that case, the buckling will be uniform throughout the section, but that may not be the case all the time. For example, let's have a look at this beam, right? So in this beam, this end is fully restrained, this end is fully restrained. In here, it is a laterally restrained only. That means it might just be connected to the purlin, cannot move laterally, but it can still twist. That's fine. So you have load through the purlin as it is, right? Downward load. Now, if you draw the bending moment diagram for this beam, you can see here, the bending moment diagram will look like this one. Good. Now, in this bending moment diagram, let me use the different color here. In the middle portion, as you can see, there is a constant moment here. Good. So there is a constant moment in this region. So what it means is that the top flange will be in compression uniformly within that section, and the bottom section will be in tension uniformly within that section. that means it will have a uniform tendency of lateral buckling, right? The compression is uniform throughout this segment 2, 3. So in that case, alpha m equals to 1, because there is a whole section can buckle laterally, the whole section, right? Whole segment, that is 2, 3 segment, can buckle laterally. So alpha m equals to 1. There is a equal amount of lateral buckling throughout that segment 2, 3. But unlike that one, if you look into this portion 1, 2, or even 3, 4, the bending moment is not uniform. It is 0 at that point, and it is maximum at the point 2, isn't it? Similarly, it is maximum at point 3 and 0 at zero at point 4. That means the beam is not having a uniform moment. That means the lateral torsional buckling in that segment 1, 2, or 3, 4 is not uniform. Less lateral torsional buckling at this point than this point, because there is more compressive force happening at the point 2 than point 1, right? So the lateral torsional buckling will not be as severe as the segment 2, 3, because there is a uniform compressive force at the top, so there will be more lateral torsional buckling happening in segment 2, 3. But in segment 1, 2, because the moment is not as bad as in segment 2, 3, your lateral torsional buckling is not severe as in 2, 3. So you don't have to take alpha m equals to 1. So you can take alpha m, we can have some allowance for alpha m. So we have alpha m equals to 1.75 here. What it means is that if alpha m is more, then your capacity is increasing. Remember, MBX equation is alpha m, alpha s, MSX, isn't it? So alpha m is more means your overall capacity is increasing, right? So the base condition is when alpha m equals to 1, when there is a uniform moment, alpha m becomes 1. But when the uniform moment is not uniform, you don't have to take alpha m is 1. You can take it more than 1, so that your moment that you calculate is not too conservative. So alpha m, you can take it more than 1. Your capacity can be better than that, right? So that's where the alpha m coming in. So it takes into account the moment modification factor, what we call as alpha m, is a function of the shape of the bending moment itself, and it's independent of the member chosen. So independent of what cross section you are using, it depends on what is the shape of your bending moment. If your bending moment is if the bending moment is uniform throughout the length of the beam, then alpha m equals to 1, because the whole beam can have lateral torsional buckling, and that is the worst case scenario, right? Because your capacity will be least. But if your bending moment is not uniform throughout the segment length, then you can increase your alpha m so that your moment capacity is more as well. So as you can see in the triangular portion here, you can have less alpha m, more alpha m here. So overall, in this bending moment shape, your alpha m can be more than 1 in that case, isn't it? So that's how we have to take the shape of the bending moment into account using the alpha m factor. And it can be found out using table 5.6.1. Now, as you can see, there are 3 ways to find alpha m. If alpha m is taken as 1, it is the most conservative case, right? So that is the most conservative. We are assuming that the whole section has a uniform moment. That's where alpha m equals 1. It is the worst case scenario. Or alpha m can be found out using this equation, or it can be found out using the table here. So what this equation means is that if your bending moment shape is like this, so it takes into account the shape of the bending moment itself. This one is the maximum bending moment here. So whatever the maximum bending moment, you can plug in there. M star 4 is at 1/4 of that beam, that is M star 4. Similarly, M star 3 at this point, at the 1/3 of that, and this is M star 2 is again in the middle one. So M star 2 and 4 is design moment at the quarter points of the segment. So it will be here. It will be here. So the quarter points of the segment will be M star 4, and M star 2 is also here. and m star 3 is the midpoint of the segment, which is equal to, again, this is also m star 3 is also at this point, right? So find out the moments at the quarter point on either side and at the middle point, and that will give you all the three moments that you need to find alpha m from this equation, and it has to be less than 2.5, right? So 2.5 is the maximum allowance given there. Or you can use the bending moment shape given in this table 5.6.1. If it is a standard bending moment shape, you can see how it looks like, and then you can take alpha m factor. Similarly, what we described earlier, see, if there is a uniform moment, alpha m becomes 1, right? And if it is a triangular one like this one, alpha m becomes 1.75, like the examples that we did before. Similarly, for different moment shapes, you can get the alpha m factor right from there, and the maximum value of alpha m is 2.5, right? So I will do this in example, how to find the alpha m through the equation or from this table. So you can find alpha m depending on your bending moment shape from this equation. Basically, once we know the alpha m, we can go and find what would be your capacity of the section. So to summarize, your nominal member moment capacity, MBX, is given by the alpha S factor, slenderness reduction factor, multiplied by the moment modification factor, multiplied by your nominal section moment capacity, right? So MSX we already find out using yield stress multiplied by the section modulus, effective section modulus. Now, to find alpha S and alpha M, what we do is use the KT, KL, and KR factor from these tables, multiply it with the length of the segment of the beam, you get effective length. Use that effective length in the reference moment. You find the reference moment m0. Use that reference moment into this equation and find your alpha S factor. So that is your alpha S factor comes here. And alpha M is depending on your BMD shape, which is from the table itself. So based on your BMD shape, find out your alpha M. Based on the restraining condition, find out alpha S. Then you can find your member moment capacity, MBX. So that is what we have to do to find out the member moment capacity. And we will do some example problems to explain more about each step. And just to end, this is a picture from 1930s, taken in 1932 during the construction of high-rise buildings in New York. As you can see, it's a very famous picture, launched atop a skyscraper, and is attributed to Charles Ibbets. So it's quite an interesting photo there.